And by the way, we met each other in Cambridge, I believe, right?
That's probably true, yes.
Yes, that's something like 15 years ago.
Oh, that long ago.
So first I'd like to start with some introduction that Eddington wrote to his book, famous book, The Internal Constitution of the Sun, published in 1926. So he wrote that at first sight, it would seem that the deep interior of the Sun and stars is less accessible to scientific investigation than any other region of the universe. Our telescope may probe further and further into the depths of the space, but how can we ever obtain certain knowledge of what is hidden behind substantial barriers? What appliance can pierce through the outer layers of the star and test conditions within? So that was, he noted that it's very difficult to learn about solar interior. So the answer to this question is heliosismology. So that's a picture from Oxford Dictionary explaining what heliosismology is. So the heliosismology is study of the sun's interior by observation and analysis of oscillations at its surface. And similar for other stars, it's called astrosismology. And as Axel mentioned, it was a hot topic in Crimea, so that was a paper by Sever and Kosovichev in 1979, where this word heliosismology was first mentioned. But the word was invented by Douglas Goff. So that's what explanation and just what heliosismology is about. So we have this tool, and then people observed a lot of oscillations, in particular because of 160 meter oscillations. That was at very close to 1/9 of a day, so people had some doubts that they really need to go to space to observe oscillations to get rid of these periodicities. So that was SOHM was launched in '96, and so it was launched in Lagrange L1 point, so it's specifically to avoid any periodicities related to Earth. So continuously observe the Sun for 10 years, more than 10 years now. So it's a lot of data, almost the whole solar cycle. And in parallel there is also a ground-based heliosismology network. So they have 6 stations around the globe, various places. And they also observe continuously for more than 10 years the solar oscillations. But of course quality from space is much better. So this picture of that I downloaded last night, so one of the last pictures of the Sun. So you can see it have a sunspot, but basically the Sun is quiet.
So do you know where now is north and where is east?
North is up, yeah.
Yeah. And the sunspot is moving toward
Yes, yeah, I'll show a movie. Yeah.
towards us now.
Yeah, so that, and of course, it's related to magnetic field, so we know that this is magnetic field, and at the same time magnetic field, and you can see it's regions of strong positive negative polarity magnetic field. If you look at the same spacecraft, we also measure in different wavelengths, so that's that's a temperature of about 100,000 degrees. It's in solar atmosphere, so we can see that a lot of heating have magnetic field. You can see also what's called atmospheric network, is created by large supergranular cells, essentially magnetic field. There is still magnetic field that we don't see in magnetogram, but it's everywhere around, so that it's still concentrated here. You can see prominence, it's nice pictures. And if you go to high temperature, that extreme ultraviolet at the 1 million degree corona, then you can see loops connecting magnetic field of different polarities. It's quite interesting. So it's even higher temperature. And this is 2 million degree, so it's even some reason it's overexposed here. So it's really the magnetic field that hits corona at a very high temperature, so it's 2 million degrees. So it's the current picture of the Sun. And I actually wanted to see a movie, so there's a movie of the past months. So you can see the Sun is quiet, but sometimes there appear sunspots. So people observe these pictures since Galileo already for 400 years, and we still don't understand what is in the sunspots. So Galileo made the same pictures 400 years ago. That you can
So why does it move actually not? It should not normally move westward, right? The Sun is moving westward if right and left are interchanged.
No, it moves in this direction. It moves from left to right.
Sun moves like this.
This is called east and this is called west. It's opposite to. So that's evolution of solar magnetic field. So that's what.
So it is correct. Why did I think otherwise?
And if you look at also the coronagraph, now the Sun is a small circle here, and it's moving. It's also a recent moving. You can see planets here. I don't remember that
No, also
Jupiter and Venus, I believe here, that were two planets here, and you can see also solar wind coming out of the sun. So it also that what last month, so the sun is quiet, so not much solar wind coming out. And that's some interesting picture, since Radar is interesting aggression. So it shows that two comets coming to the sun, and then there's an explosion, big explosion. After they hit the sun, there's a big explosion. It happens often, and people still debate, is there any connection between when comets hit the sun and explosions happen? So we still don't know what its relation is. But it's maybe coincidence. Most people believe it's coincidence, but it happens so frequently. It's about 1,000 comets already observed by SOHO.
Yeah, but I mean, is there a connection really between? Does it often happen that there's a
It
connection?
happens frequently, yeah.
Uh-huh.
At least every time I see comet, I also see me. But see me happens without comets, so
Yeah.
that
Yeah.
it's several a day, so I don't know really
Mm.
if it's coincidence or not. And actually, nobody studied this. It's quite possible that there's some
Yes.
comets they cause some instabilities and all that, then make them stable and all that.
And here we have two comet fragments, right, from the same.
Yeah, you can
comet?
see two different comets. Yeah, that's
Two different ones. Two fragments.
So that's kind of accretion about it. But more often we can see explosions, so that the solar wind, that continuously. So accretion is not that common. And of course, that when flares happen, that what some loops are heated, that we have X-ray radiation, so that it's really. So what the purpose is to really here is most to understand the origin of magnetic fields, origin of sunspots, and I'll briefly review what we know about the sun. So that's the structures we believe that what you know about the solar interior. So that's core, nuclear reactions, 15 million degrees here, and then energy transported by radiation, and at a radius at about 70% of solar radius, it becomes unstable. So the energy transported by convection, and so that's what this turbulent convection layer actually excites solar oscillations and generates magnetic field. So how it generates, we don't know. So that's what the goal to understand how magnetic fields are generated in the convection zone by dynamo, create all these magnetic fields, sunspots. So that was it's a big puzzle. So there's some questions that what we look in heliosseismology, where we try to understand chemical composition of the sun, and temperature distribution, density distribution, also rotation rate inside the sun, gradient circulation, structure of convection, these convective cells that we see on the surface, what the structure is, depth, what the source of solar magnetic fields, how these sunspots are formed, and what is instability that causes mass eruptions. And also what practical question if we can predict periods of high solar activity. So let me show that the picture, that's what the main tools that we use. So here, if you look carefully here on this, you can see that central part is oscillating. So that's the Dopplergrams, that's the real data. That's the Dopplergrams, and here the central part. Just the central part, you can see also oscillations, you can see the small scale convection. So it happens that we have this turbulent convection on the surface, and it excites acoustic waves. Like always, the turbulence excites some noise, some acoustic noise, so that's kind of acoustic noise. So these oscillations are very stochastic, and the period is about 5 minutes of these oscillations, and they're almost radial. So you can see that only, if you look, that only because you see line of sight velocity with Doppler shift, the radial, only the central part of the sun oscillates. And you can see kind of stationary pattern here, that's supergranulation, supergranular cells. And here you can see this patch that flows, stationary flows in sunspots in active regions. So that's all, everything is stochastic here, so that what it's difficult to analyze, so we have to need to understand how so these waves are excited near the surface, they propagate to the interior, but they're very stochastic, so we need to develop some procedures how to learn about the interior of the sun. And they show this movie that was how we increase resolution. So you can see sunspots, very small sunspots. And now that what picture is taken from Swedish solar telescope, La Palma, and you can see that it's a nice picture of granules. So the oscillation is actually excited in dark lanes. So that's the granules, the size of about 2,000 kilometers. You can see that's very complex structures, magnetic field, very, very small sunspots. So oscillations are excited by downflows in dark lane of granulation. So that's established now. So that what some simulations also show this. So this actually observation, they show some darkenings and show some essentially downdrafts in dark lengths of granulation, and these downdrafts, they excite the maybe supersonic even. They excite acoustic waves, but randomly. So and sometimes we can see that what in solar flares can be impulsive source. So that one of the events when the solar flare excited ripples from the sun. So you can see just ripples like water waves. So that this movie was essentially enhanced because this amplitude, this amplified the factor of 4 this wave. So that was flare at the beginning and then this expanding wave. So you can actually look at, you can measure the speed of this wave. And so that what you can compare with water ripples, because in water you can see through a storm, you can see similar ripples. So what's the difference between these? And the difference is that the water wave, they propagate with constant speed. That's determined by dispersion relation of water waves. And the solar wave, solar ripples, they accelerate with distance. So if you make a space-time diagram, so then I just average over angle and plot it as a function of distance from central part and time, so that's the signal. So you can see this reach, that's the ripple that created by these waves, excited by solar flare. And you can see changes is slow. And so for larger distance it takes less time to propagate a particular distance, so that means that the waves accelerate. So it actually accelerates from 10 kilometers per second the speed to 100 kilometers per second. So what's the reason for this? The reason is that these waves, they actually don't propagate on the surface. Even we see like a ripple propagating on the surface, but the waves propagate inside the sun. So what happens is that when you have impulsive source here, then acoustic waves propagate everywhere. And the first arrival, if you watch here for wave signal, the waves, the fastest waves, they arrive through the interior, because sound speed is high in the interior, because sun is hotter inside and sound speed is higher. So the waves, they, according to Fermat principle, they choose the path that corresponds to the shortest time between 2 points. So the shortest time goes through the interior. So we use this property for heliosismology. So what we do, we measure the travel time for different distances, we measure the travel times of waves. And then from these travel times, if there are some flows here, or some variation of sound speed, then we can actually recover these variations by doing seismology like seismology. The problem is, of course, that these events, the solar flares, they're not very frequent. It's only a few of them. We observe and can see clear signal. So we have to extract this signal from turbulent random stochastic excitations. And this is done by calculating a cross-covariance function, cross-covariance between different points. I'll show this later. But the principle is that the waves are excited by convection of solar flares. The acoustic waves, they propagate through the interior. And they are refracted because the sound speed increases with depth, and then come back to the surface. They can refract again, and then after several reflections they go to the far side of the sun, and we can actually see some spots on the far side of the sun.
You mentioned before that comets hit the sun.
Yes.
Do you know whether in certain cases when comets do hit the sun, they also excite ripples or not?
No, unfortunately we don't know this. We try to look at this, and what happens is that to observe these ripples, because the SOHO spacecraft is far from Earth, it's 1 million miles away, and we need a deep space network, we need big dishes, so and this is very expensive, so we have continuous contact with SOHO only 2 months a year. And it happens that we have this contact during these 2 months when there are no comets, they come at certain periods. So we haven't been able to actually check this.
I see.
So that's again, this illustration that how that to show, because it's important for just for the whole heliosismology to understand how these acoustic rays propagate, so that they propagate to different depths depending on the takeoff angle, and since they're stochastic, so they propagate everywhere. So that so the measuring travel time, so on. Also they establish some resonant frequencies. You can see that there's a reflection, so the wave reflected here, and then they come back. So they can travel around the sun and establish a resonant oscillatory pattern.
But it's with respect to depth, not with respect to the closure of the path.
It's with respect to depth, yes. So what you can do, you can take the movie that I showed, this movie of solar oscillations, and then do three-dimensional Fourier transform. So project on spherical harmonics, and then the Fourier transform in time, and then plot this power spectrum as a function of angular degree of spherical harmonic and frequency. And then you can see these resonant frequencies. So it's a pretty nice picture. So this is a 3 millihertz period of 5 minutes. And the spherical harmonic degree from 0 to 1000. And that's the lowest reach corresponds to surface gravity wave. It's called F mode. And other reaches are acoustic waves that propagate inside. So that's, you do just it's a power spectrum. So that's what it's called global heliosysmology. Then you can measure the frequencies, very accurately measure frequencies of these modes, and then just relate frequencies to the structure of the interior, solve inverse problem, and then recover the sound speed potential distribution inside the sound. And another technique that what I mentioned, we can measure also travel times. Then we have to calculate the cross covariance function. So I measure oscillatory signal at 2 different points, separated by distance delta, and with some time lag, tau. Then adjust its cross correlation, cross covariance function. And if we plot this cross covariance function as a function of distance delta, so this is delta, and this is time lag tau, then you can see also a set of reaches. And they correspond to acoustic waves propagating between, say, if you take a distance 50 degrees on the surface. So we measure oscillation signal at 2 different points at 50 degrees. So that's the sun. So we have 2 points. So we just cross-correlate signals at 50 degrees. And we can see this kind of picture of a wave packet here. So this corresponds to waves that propagate directly between these 2 points. Then we can see another reach at larger time lags. And this corresponds to the waves that propagate between these 2 points after one reflection. So that was direct signal, and also there's some waves that come, they propagate, it takes longer time to propagate. So that's the origin of these multiple regions here. So that explains again the same picture. And then we can, of course, say use some simple theory. We can use Fermat principle and relate to calculate how the changes in travel times related to perturbations along these ray passes. So that essentially the travel time of acoustic waves is affected by variations of sound speed along the ray path, the delta C, and this is the phase speed, inverse phase speed, K omega. It's called slowness in seismology. And the second term, it's a advection term for the waves. So there's some flows here, then also the change travel times. So then to separate these 2 terms, what we do, we measure the travel time, because we have this the whole picture of oscillations everywhere on the sun. So we measure the waves they propagate from point A to B, and also from point B to A. And then if we take the difference of the travel times, then we cancel the first term. So then we can recover the velocity distribution. If we take the mean travel time, then we cancel the second term, and then we recover sound speed. So that's the principle. In principle, we can measure there's another term here that depends on magnetic field. And magnetic field, then we need to it's a bit more complex measurements, because then we use property of anisotropy of acoustic waves, because waves propagating along magnetic field, they propagate with different speeds and waves across the magnetic field. So it's impossible to look at magnetic studies, to measure magnetic field directly. So that's the picture of standing waves. So that one of these normal modes that I showed in the power spectrum. So you can see this is spherical harmonic, L equal 20, M equal 16, and this is with depth. I forgot what is, how many nodes here, but that's a resonant wave with depth. So that actually notice that here the turning point somewhere here, this depth. And they establish this nice resonant pattern, so that's what And also then the theory is very similar to quantum mechanics. It's described by 3 quantum numbers. So that's the theoretical spectrum of solar oscillations. If you just calculate the normal modes of a sphere of the sun with solar stratification, then we have acoustic waves. So that's again this L, spherical harmonic degree. This is frequency. Then there are internal gravity waves, buoyancy waves, that are restoring forces, buoyancy here. And there is a surface gravity wave, it's called F mode. This is like a water wave. So 3 types of waves essentially here. And what is observed now, we observed only this part. Here the amplitude is so low, it's very difficult to observe any oscillations with frequencies below here to 1000 microhertz or 1 millihertz. So essentially that was, nobody observed G modes. Even Boris is computing G modes excited by convection, by overshoot. But no observations here.
But is that because you can't access those frequencies or because the power is really too low?
The power is too low.
Yeah.
No, they said it's frequency.
Because you have this red box which suggests you cannot.
160 meter oscillation, by the way, it's 104 microhertz. It's here.
Yeah.
So it should be one of the G modes.
Yes.
So that was one of the theories for this. But really, we don't see the spectrum.
Mm. And of course, they would be extremely evanescent. So they would, by theory, have vanishingly small amplitude.
Yes, evanescent, but you can see, what was the hope here, that you can see here that was what's called avoided crossing. It's like in atomic physics.
Yeah,
so you can see this cross, this mode cross,
yes.
but it's no real crossing here, because this mode goes here, and then, like in atomic physics, it goes here.
Yes.
So here it's no crossing, it's just in this picture. And here the some modes is mixed behavior, so they behave like P modes. And here at the low L equal 1, they behave like G modes. They have mixed behavior.
Yes.
So now that most of the effort is to observe these modes. So they're still very sensitive to solar core, and they have sufficiently large amplitude at the surface.
I see.
So that's what.
Yes, indeed.
And of course, all these G modes they're dumped very quickly because they have they're also very high radial order. They're very evanescent, as I mentioned. So they only hope to observe say T equal 1, some dipole modes or quadrupole modes. So that's these frequencies.
So when Boris does his global simulations that you may have seen, then he may be actually able to see those as a modification of the P modes due to G modes.
Yeah, that
very
would be
small
interesting. Yeah, interesting to
So
look.
that will be really interesting.
Yeah. What he has to do to calculate, he has to calculate the power spectrum of oscillations at the surface.
Yes.
I think that's very interesting.
Yes, he will do that, yes.
So this is the observed frequencies. So I show the theoretical, now that's observations. So you can see that stop 1,000, so that's what. And here that's error bars. And the error bars here, that's really 1,000 sigma error bars. It's extremely precise measurements. We measure frequencies, solar frequencies more precisely than we know the gravity constant. So this is 1,000 sigma error bars. So we need this precision to study structure of the sun, of solar interior. And here that's a sound speed profile. And this is not a sound speed profile, it's a difference between the sound speed that we obtain from these frequencies relative to the sound speed of the best standard solar model. So the solar model was also evolved and tried to adjust to Healy seismology, but still there are significant differences. So in particular here, so that's, as you can see, it's only less than 1% the difference in sound speed. So you can see there is a peak at 0.7, and to remember here was the base of the convection zone. So that's what, there is some additional, so to explain, there's some additional mixing at the base of convection zone, and it's probably overshoot. So I believe that this is an overshoot effect, convective overshoot, like what Boris is modeling, overshoot at the bottom of the convection zone. And also there are some differences in the solar core that we don't understand. They can be explained as some partial mixing, which may happen that during the solar evolution. Because if you use standard theory of stellar evolution, calculate sequence of solar models, and then look at stability of these models, it turns out that these models are unstable for most of the life of the sun. And then stable G modes unstable because of reactions to helium-3. in the core. So there might be some mixing that happens during solar evolution, and that we can see still some signatures in the solar core. And there is some difference here that in the convection zone, because you don't describe the solar model use Michelin here, it doesn't describe properly properties of solar convection.
But this is the old metallicities, yeah?
It's all, yeah, I'll show you new metallicities, yes. I don't know how much time I have, but I'll try to show some quick with some kind of review. So that's again this illustration of this picture, the solar model. So you can see this red is where we have enhanced sound speed, and blue where we have low sound speed, and also we can measure latitudinal distribution of the sound speed. And this sphericity of the sun, it's only some very shallow layers, that most of the sun is spherical. So you can see again, this is called Pahak line. So basic convection zone, we can see enhanced sound speed.
So the pole was hot, you saw that.
What?
Yeah, the pole was hot. Yes.
The pole, yeah, that was
And then
solar
it's-
minimum. I made this picture at solar minimum.
And then it's hot. And then it's hot again at the equator a little bit. That was interesting.
Yes, yeah.
It's cool at the surface.
And this changes the solar cycle distribution. This is this made in '96. This picture.
Okay.
How about in the tank line? Does this also change with
That's line. No, this is. No, it doesn't. It changes, but it's controversial change. Not that significantly. This deviation that was about. It's almost spherically symmetrical, and it doesn't change much. And it changes at a level of 10 to the minus 10 times smaller.
Okay, this would be a few kelvins or something like that.
Yeah,
If you translate it,
yeah, and then.
Because this would be important for the differential rotation for differential rotation models.
I'll show rotation. Yeah, I'll show rotation is easy to measure. Yeah. So rotation is measured because it's a differential measurement. So now it's a distribution of. So one of the important results of heliosismology that was discovered that when we try to match the sound speed profiles, so that we discovered that you need to match the sound speed profile, you need to include solar model gravitational settling of heavy elements. So here it's a distribution of hydrogen, so that we have less hydrogen in the core because hydrogen is burned into helium. And there is some also that was this gradient, that's at the basic convection zone. This is because of gravitational settling of heavy elements. So the nuclear burning and that's helium settling here. And now what recently was people tried to, so it was, the agreement was very good, and everybody was happy except we have this bump to the basic convection zone, but there was a lot of people work on this, trying to explain this bump, Pahak line. And then suddenly 2 years ago that Asplund published papers where he tried to estimate abundances of the sun by using numerical simulations, novel Einstein simulations for solar atmospheric structure, and then try to match the spectra that from this model to solar spectra. And what he came that we need to decrease substantially the abundance of oxygen to match this numerical simulation. So previously people used just hydrostatic model of solar atmosphere to obtain abundances, to calculate the spectral light and then to match the observed spectral lines. So that was the previous oxygen abundance. And then Asplund said that it should be a factor of 2 lower oxygen abundance. So that leads to revision to what is called heavy element abundance. And that changes dramatically solar models.
So the oxygen abundance, yes, is almost a factor of 2 less, but the heavy elements otherwise are less than a factor of 2.
Yeah, because there are some other elements,
Yeah.
iron and all this mixed together and all what's called Z. All heavier than helium. So X is hydrogen, Y is helium, and Z is.
And they're not so tightly covered, these other ones. I mean,
Yes,
naively one would think
yes,
they are.
So then what, remember that I showed the picture, the deviation of sound speed, the function of radius, and this is actually this picture, the same picture that was reproduced here. That was the agreement we had with all the abundances. And now with absolute abundances, it changed dramatically, so then we have a huge difference in sound speed. It's not really possible to explain by any other mechanism. You have to revise radiative transfer theories here, and usually this radiative transfer, that was called opacitive, they calculated quite accurately from atomic models, and people are quite confident they calculate correctly. So it's really very difficult to explain this peak. And there was some discussion recently that maybe abundances of some other elements are wrong, like neon abundances. If neon, that what John Bacall did before his death last year, that were trying to increase neon abundance on the sun, and it kind of compensate for this contribution to opacity. That's a logarithmic derivative of opacity to abundance of different elements. So if you decrease, say, oxygen abundance and increase neon abundance, then you kind of compensate with compensation. So then it's possible again to reduce, by increasing neon abundance by factor 2.5, it's possible to reduce this peak again to the values that we had before.
And the only reason they use neon is because neon is otherwise not observable, right?
Because it's not well determined, yeah.
Yes.
You cannot play with iron because iron is very well determined. Yeah, that's the whole reason. But then people criticize this a lot, so that because then they try to, and also that was some results by Drake, and then they say X-ray observations in nearby stars they show also increase in neon, so some excitement.
Is that believable, you think? I mean, is that significant, this result, you think? I mean, it sounds important, of course.
It sounds important, yeah, I don't know. So it may be important, but now people become more skeptical because when you use it's really numerical models,
Yes.
and to calculate by yourself, you know that you don't quite model solar turbulence. So usually numerical models, you have high turbulence velocities and
Yes,
sun.
of course.
Just compare the power spectrum, right?
Sure. But there are so many other
When you
reasons
have
as
high
well.
turbulence velocities, then you have the broader lines,
Yes.
and then of course the change its abundances, so that you have to believe in numerical models. So
But
now people become skeptical about this, so that
about this theory, about the models.
about the use of numerical simulation.
Sure, it should be tested. I mean, it's amazing that, of course, so many citations have been generated on this paper. I mean, over 200 or maybe close to 300.
Yes, yeah.
It has been a very important field of convection, of course, in the history of numerical hydrodynamics. One of the most cited papers, perhaps. And still, there's only one group in the whole world who has really been able to produce such a thing.
Yes,
Nobody else yet. And everybody relies on this these days.
No, it's very
Of course,
important.
naturally to be
I think it's one of the
skeptical.
goals, because now these simulations, not the standard simulations, they reproduce granulation like real stuff, so it's very, very close to real.
Yeah.
But there's still significant differences. If you compare the power spectrum, so we can see a lot of turbulence is much higher than real sun. Turbulence velocities are higher in simulations.
Yes.
So that
Not really so much, of course.
And now that's a differential rotation, so that we know that the equator rotates faster than the poles, and that generates a magnetic field. That's a movie that I like that illustrates the solar dynamo, how we wrap magnetic field lines around the sun, and then generate some buoyancy, generate loops that appear on the surface. And that's basically all we know about the solar dynamo. We still don't know
So
what
how have you done this movie?
What?
You just put in some differentiation and some other.
It's not mine. It's not mine. I found.
Who has done it?
I don't know.
It's pretty cool.
Yeah. So what's interesting that there's a famous butterfly diagram. So the sunspot appeared at the beginning of the cycle appeared at high latitudes. Then the zone of sunspot formation migrates to low latitudes, and also this picture repeats every 11 years. So there's no explanation for this. So that's belief it's maybe dynamo wave here. That's what can be produced. And it's more complicated if you look at the distribution of the magnetic field during the solar cycle, and you can see the butterfly diagram there where sunspots are formed, but also some flux is transported by something in dynamo theory, dynamo wave, and some people believe it's a meridional flow transports magnetic field. So sunspots appear at bipolar regions. There's a positive negative polarity here, and the magnetic field of falling polarity sunspots is transported to the polar regions. and reverses polarity every 11 years also. So the polarity, the polar field of the sun is reversed around the solar maximum. So that's pretty amazing picture. So we can see that how that magnetic field, we have this turbulent medium, and that's again interaction between rotation and convection generates differential rotation. We still don't understand why it's a differential rotation. These models, numerical models, don't reproduce well differential rotation of the sun. And in addition to this, it generates magnetic field. It's a dynamo, and dynamo is so regular that every 11 years it creates opposite polarity, flips polarity. So that's a model of differential rotation. So that's observed differential rotation that we know from heliosysmology. So that differential rotation is confined to the convection zone, and the solar core rotates almost uniformly. And there's a region of sharp transition called tachocline. That's a numerical model. In numerical model, they also have this feature that rotation is constant on cylinders. That's a Taylor column, Taylor-Kalman columns. So it's very difficult to get the same shapes as we observe. So still, I believe it's still not resolved. Also, the tachocline is not quite yet reproduced. So that's, I think that's a movie that was Sasha Brown made with Yuri. So then the model convection, that's a full 3D simulations of solar convection, they reproduce the differential rotation, but still they don't reproduce the same rotation is constant on cylinders. And convective cells, they are called banana cells mostly, so that's what we call it.
In these models, they don't yet have the overshoot layer below the convection zone.
No, not yet, but they're getting close. I think what's happening.
No, I think now.
Salt and burn,
Yeah, that's right. But then they imposed some kind of temperature, latitudinal temperature gradient.
Yeah, they don't impose some temperature gradient that they can get closer to the observer, but still they don't quite reproduce the rotation. So that's another picture of that was solar rotation that we observed with heliosysmology. So what's interesting also that what the solar rotation changes the solar cycle. So the first meridian circulation, which we observed only near the surface, we have not yet measured reverse flow that we expected at the bottom of the convection zone. But we observed meridian flow near the surface. And it's interesting, these bands, slow and fast rotation, they show how differential rotation changes the solar cycle, how the magnetic field interacts with rotation. And here we plot this they call torsion oscillations, so that the rotation, the velocity of rotation of the sun is 2 kilometers per second, and these flows, these jets, fast or slow rotation, that's only a few meters per second. Here it's shown in nanohertz, that's rotation rate, but that's about 10 meters per second or 8 meters per second. These flows. So here there are some bands of fast rotation and slow rotation. So when you subtract the mean rotation of the sun and plot the function of time, so we can see that there are some zones of fast rotation and slow rotation. They migrate, they make a similar butterfly diagram. So actually the sunspots appear as a boundary between fast and slow rotation rates. But we don't know why. We don't know if a magnetic field causes this fast slow rotation, or it's somehow that's a different mechanism, and also there's a big change in rotation of polar regions. So that's what in heliosysmology you can measure this is depth. So that's near the surface, it's 1% below the solar radius, then it's 3% below, 5%, 8%, and this kind of becomes it's noisy, this picture, so we don't know what actually how deep these oscillations are. It is believed currently that at the polar regions, these variations of rotation rate, they go through the whole convection zone. They're much stronger and go to the basic convection zone. And in mid-latitudes, these zonal flows, they're more shallow. They don't really go through the whole convection zone.
But they, as far as the time delay is concerned, they come first at lower depths and then they propagate.
Could be, I don't know. You can look at these
forward in time.
They change with depth, they look like they propagate. That's
with height outwards.
So they need also some imagination. So that's so it's quite noisy. So it believes that, that the magnetic field actually of the sun is generated at what's called tachocline, where the rotation changes from differential to solid rotation. And what people try to look at was how rotation rate changes in the tachocline with time. And first, what was found, there are some periodicities. Everybody expected a period of 11 years, of course, but we don't see it. Instead, they see a period of about 1.3 years. And now they found out to continue. I didn't update this picture, but then it's kind of disappeared at solar maximum. So it was the solar minimum here in 96 and 2000 was solar maximum, and this constellation they kind of disappeared. And it's not clear if the new solar cycle will continue or not. So this movie illustrates again the variations in solar rotation rate that we see. So we can see this migrating bands of fast and slow rotation, or differential rotation. In the tachocline, there are some variations this period of 1.3 years, which are not regular. So that's not clear if they're really real or not. So now it's a lot of dispute about this. So that was result from global heliosysmology. If you look now at local heliosysmology, with the travel times, then we have much richer picture. So here actually that was a flow map of flows below the solar surface. So it's a depth of about 2 megameters, 2,000 kilometers below the solar surface. We measure so we can see the small arrows. So we have this, it's only one small portion of this map. So we can have a very detailed picture of subsurface flows. And the background is a magnetic field, a surface magnetic field. So here first we can see this convective cells, we call supergranulation. And we can see that how the magnetic radiation of the subsurface flows changes. So the most typical, so you can see this decaying sunspot, and what's mostly we see outflows. But typically around sunspots we can see inflows like here. So a lot of information here. And actually what you can do, you can take this, obtain these maps, the whole sun, then you can take, say, one component. You can take east-west component, an average over longitude, and then recover rotation, so the variation of solar rotation. Or you can measure meridional flow, so there's a lot of information here. So that's a low resolution map, when it averaged, or to some low resolution, we can see again some conversion flows around active regions, so you can see the complicated flow patterns. If you look with depth, so typically we see some conversion flows around active regions in subsurface layers, but in deeper layers at about 10,000 kilometers below the surface, you can see outflow. So there are some circulation cells around magnetic regions. And what's interesting is that this dimensions that we observed in meridional flow, and these circulation cells around active regions, they actually affect meridional flow, and they affect magnetic flux transport to polar regions. So this shows that how the velocity of meridional flow, so that's equator, so this flow goes to North Pole, goes to South Pole, solar minimum, but when solar cycle, so that was solar, there's no magnetic field of the sun here. And when magnetic field appears, this picture changes. So it affects magnetic flux transport.
So which depth was that? That's near the surface, right?
That's near the surface, it was 2,000 millimeters.
Oh, and negative was to the left was at high positive northern latitude.
Yes, yeah. So what's interesting, so that what for people that would try to predict the next solar cycle, that's actually what high value of this, so that what NASA estimates the prediction, the cost of the correct prediction cost about several $1 billion. So
that's an amazing story.
Because knowing the number of sunspots, they can predict the parameters of Earth's atmosphere, and that affects all satellites. So now we are here.
The Hubble Space Telescope.
So the number of sunspots, a function of time. Now we are here again at new solar minimum. So we started here. So we have a complete picture of this solar cycle. Nobody was able to predict actually this solar cycle. Most people believe it will be higher. And now people are trying to predict the next solar cycle by using dynamo series and data simulation that we discussed in Bern. So that was, but that's really very long. Also we know that in 17th century was a period when sunspot disappears, and of course it was very cold and snow particularly that was everything was frozen here. And that's what people expect, that what I knew is called Maunder minimum. So what we know about this minimum of solar activity was several minima, this grand minima. The last one was Maunder minimum in the 17th century. For 50 years was no sunspots. And if you look at periodicity, that a lot of people would expect the net minimum. Maybe it's coming.
Somebody predicted.
I mean, it was kind of a small minimum in the 1800s again, right?
Yeah, there are some small, but but not this grand minimum. When for 50 years was no sunspots essentially.
Sure.
And was what's called Little Ice Age, was very cold in Europe. So it also what we're trying to understand the structure of sunspots. So essentially that's what people discuss, the two models of sunspots. One is called monolithic, you have just magnetic flux tube, it's compressed by convection and then it expands to the atmosphere. But then you think how it can hold this, because you have this magnetic field is concentrated in spots on the sun. Why it's not distributed over the whole surface when it's all turbulent? Turbulence should spread around. And then Parker suggested that maybe there are some flows below the sunspots, and they would then just dynamic force will hold these magnetic field lines together. We call it cluster model, because it's otherwise very difficult to explain stability of sunspots and their formation where it's concentrated. So I'll show what we see now by heliosismology. So you can see the solar oscillation, that's actual data that we observed with SOHA. So then they analyze these oscillations around sunspots. You can see a small, it's called pore appeared below sunspots. Now I make this upper boundary transparent and show the sunspeed distribution below sunspot. So you can see that below sunspots we can see that area of low sunspeed extended to depth of about 4 or 5 megameters. And then we can see a region of high sound speed. So the sunspot is cool because magnetic field inhibits convection, but not through the whole sun. And you can see some connection to the pore of same polarity, and some kind of fingers at depth of 5,000 kilometers. And now I show that the flow pattern that we derive also by measuring the travel times. So indeed we can see below the sunspot we can see convergent flows. These convergent flows, they cover the range of depths that's up to 4 or 5 megameters. So the same that we can see the cooler part. So we can see low sound speed, and we believe the sound speed is low because temperature is lower. And for some reason that we can see that for high sound speed, maybe that heat flux is some kind of blocked here, because magnetic field inhibits convection and blocks the heat flux. That's why sunspots attack. And to see this picture, it's amazing that you can see similar, the flow pattern was suggested by Parker to explain the stability of sunspots. So maybe that was some connection, and actually people tried to do some simulations. That what Neil Halbert he was trying to do. I believe it's cylindrical, symmetrical, or some kind of quasi 2D simulations. And you can see also these flow patterns that around that magnetic field is concentrated. And here also see a divergent pattern at larger scales. But what's important that there is also convergent pattern that we see by heliosismology. So we're trying to match these observations to numerical models. So this published by Halbert and Rakic. Actually this was observations and models that were done at the same time independently. We just know about each other results. And here you can see that we have a similar structure of the temperature here. Also two-layer structure in simulations, and also convergent flow. And here we can see a different scale, because of course in numerical simulations there was no scale. There's just much horizontal scale to have similar horizontal scale here, but in fact they had just a small pore here. So that was, I think it's just it can be scaled differently. This picture that they have similar depth.
I see.
So there's some similarity and a lot of what can be understood. Also, we try to catch this emergent magnetic flux. So we know that magnetic fields generate somewhere deep in the convection zone and then emerge. And here we try to image emerging active region here. So that's the difference between. So we need to, because we use these stochastic oscillations for measurements, we need some time to accumulate, like exposure time, to accumulate the signal. So typically we need 8 hours of measurements of acoustic waves to generate one of these pictures. to measure travel times. And here you can see the difference between frames is 8 hours. So if you can see that how the active region appears, it appears very rapidly. So that was, here was nothing here. And then we can see that some first signatures of emerging active region, very weak, and the magnetic field appears on the surface. This is magnetogram, and then it becomes stronger, and then it increases very rapidly. So we can estimate the speed of emergence here. So we can see it here. You can see first flux at the bottom of this box, which is depth 18,000 kilometers. And we can estimate the speed is about 1 kilometer per second. So it emerges very rapidly. So that's what picture of emerging magnetic flux. And some interesting active region appeared in 2003, October, November. So that was emerging active region. And it was another active region that gave a lot of solar flares. And here I show that some images. So this was active region that was at the bottom of this movie, and I show some images of emerging active region in the middle of this box. So you can see it appears, it forms very rapidly, and then forms this typical two-layer structure that we see below sunspot. And what's amazing that at the end of this we can see a kind of a loop-like structure that we expect from inversion loops from the bottom of the convection zone. So I showed this the picture of sun quakes, and it was also interesting. It was observed in 1996, and then for many years I didn't see any events like this. And why it's interesting, because it's interesting to understand how the solar flares, so of course there's no storm, there that some high energy particles that interact with plasma of solar atmosphere generate shock waves, some kind of explosion, how that it finally creates acoustic waves, how they create these acoustic waves. But it turns out that what we can see first at the beginning of this movie, at the center, you can see some kind of a shock wave propagating from the atmosphere, propagating down. And these shock waves correlate very well with hot X-ray flux. So somehow it's correlated, caused by high energy particles. And here it's a standard picture of a solar flare. So how the solar flare happens, it's in some way in the corona. It's a process of reconnection of magnetic field lines. And during this reconnection, the particles are accelerated to high energy, electrons and protons, and they propagate along the magnetic field lines, and they hit the solar surface, causing heating of the solar surface. And that's two sources of, again, hot X-ray radiation here. And they cause evaporation of plasma, and because there is evaporation, there is also, because concentration momentum, there is a momentum down, there is a shock wave propagating down, and that causes these sun quakes. So again, this picture that illustrates that the electrons are injected into the magnetic flux tube, then they hit the chromosphere, causing the high pressure region, which expands, causing evaporation. That's what you can see these mass ejections, coronal mass ejections, and also photospheric shock waves. So that causes this seismic waves. That's what I did some long time ago, some simulations of these shock waves. And what's interesting that we observed in 1996, and then for a long time we didn't observe any, and then 2003 they appeared again. So observed in 2003. So that's a movie which is not enhanced in any sense. So this is just Dopplergrams. You can see convection here, you can see the solar flare, and if you watch carefully, you can see these ripples propagating. They're weaker than was before. You see these ripples?
Yeah.
So that's what, this is just raw data, they're not enhanced, not processed. So you can see these wavefronts here. And you can see the same, you can construct the time-space diagram that also shows the same acceleration. And then it's 2004, you can see flare in the middle, and now you can see waves propagating, so that's it's interesting to watch this. And here the strongest event was in 2005, you can see this wave propagating here. So we can do a lot of analysis of this. It's quite interesting to study, and particularly look how this is related to hot X-ray sources and also some gamma ray sources observed here. That we have another spacecraft, RACI called RACI, which measures X-ray and gamma ray radiation of solar flares. So it's quite interesting. So that was. But what's amazing that what I don't have this picture, but the distribution is with solar cycle. So the first event was in 1996, and it was the last flare of the previous solar cycle. Then the new cycle started. We didn't see anything until declining phase of this solar cycle. So there's something special about the end of the solar cycle. The flares are different because the magnetic topology is different. So it's about the future of solar. So that what now we're preparing, as I mentioned, that we have only 2 months a year continuous data because SOHO was launched in Lagrange point to do some low resolution heliosysmology. So we do continuously. We bring data on board, so we make images with CCD 1000 by 1000, but because we don't have telemetry, we have to bring down to 200 by 200. Transmit continuously. And only 2 months a year we have continuous contact with SOHO when we transmit the full resolution data. And now what we plan to prepare the so-called Solar Dynamics Observatory. And here we'll have a much higher resolution, so it will be launched on geostationary orbit, so the data transmitted continuously. And with much higher resolution here, again, that was 3 telescopes here, that was our telescope is to measure magnetic field and Doppler velocities and solar oscillations. So now we have 4000 by 4000 CCD, 16 megapixel camera, which will take images every 3 seconds. So total amount of data will be about terabyte data per day to analyze those, to look and to understand how sunspots are created. So it's an amazing project. So it also will make some pictures in ultraviolet and measure radiance. So that is pretty cool. So that here, that's what picture from that what I made for our proposal that shows that all these pictures that I showed you before, because we want to study everything that we learn, but in more details, and to understand what generational sunspots and meridional flows and differential rotation. Also, apparently, it's important that with heliosysmology we can see the far side, sunspot on the far side of the sun. That's important for prediction of the space weather. And so that's a data analysis plan that we're working now, so how to process the data. So we have a terabyte of data here, of filtrograms, and then we can generate Doppler velocities, magnetograms, vector magnetograms, and then do different flow maps, sound speed maps, and try to understand what essentially the origin of solar magnetic fields, how they evolve, how they generate solar flares. And also that what recently was launched, it's a Japanese satellite called Hinoda. It has also has optical telescope, and it makes pictures with very high resolution. So just to look at very details, to look at individual flux tubes, or structural sunspots. And here one of the first movies from Hinoda, they observed Mercury transit. So you can see they have this very high resolution that is in molecular G band. So that's some magnetic points, that's granulation here, and you can see that was Mercury transit.
So Hinoda is the same as Solar B, or what?
Yeah, that's their name. So Solar B, it's called Hinoda, yeah.
And Yuko was Solar A, or what?
It was Solar A, yes. Yeah, I guess that's
all right. Okay,
Thank
so
you.
thanks so much for that.